So, phased arrays. Here's our roadmap. So first we're going to talk about the basic physics and math behind a phased array, how it works. We're going to talk about what you can do with a phased array, why you might want to build one, then how you can actually build one, and then we're going to talk about some design considerations you could think about when you're building one. Real quick, you just heard this, I'm Hunter. I build phased arrays during the day mostly, and I've been designing stuff for a while. Okay, so this is probably a review for most, if not all of you, but this is sort of the basis of everything that I'm talking about, so we have to go over it. Phased array, phase. So in these waves here, we've got the blue wave and a red wave. They both have the same amplitude. They both go up to the same height. They have the same frequency. And they're phase shifted apart from one another. So if we start with two waves on top of each other and we slowly start shifting one relative to the other, then we have a phase shift. And the best way to think about phase shift for the purposes of this talk is as a time delay. And we'll get into more about how that works in a minute. Before we talk about what exactly a phased array is, we have to talk about what a phased array isn't. There's a lot of things that are not a phased array. This is one of them. This is an antenna array. This is the radar. It's an AN-APG 66 radar off the front of an F-16. So this is what goes in the nose of the airplane. And the reason this is not a phased array is because we don't have phase control over each individual antenna element. Instead, the reason you do this is because you'd like to have a very directive and a really high gain antenna. So one way you can implement that is with a whole bunch of small antennas. This is a whole bunch of slot antennas instead of one big antenna. The problem now is that if we have a very high gain and a very directive antenna, if you're in an aircraft, you'd like to be able to scan around the sky to look for stuff in all directions. So instead, the way they do this is they physically move this array. If you look over on the right there, you can see the pan-tilt mechanism where they physically move this thing around the sky to look for stuff. However, physically moving antennas around can sometimes incur problems. This is, I think what must have happened here is like a limit switch or something failed on an antenna rotator, and the antenna just kept rotating and eventually crushed the waveguide. So we can avoid this with phased arrays. So there we go. I'm going to start by showing a bunch of different sort of visualizations to try to give you an intuitive idea for what's going on. I'm going to be purposely slightly imprecise from a mathematical perspective, and then we'll fine-tune it later. So this is one example of a phased array. This is a linear phased array of antennas. And it's kind of weird when you think about it. If you've got a whole bunch of antennas that on their own have a fixed radiation pattern, and you can't physically move the antenna, and there's no way to physically move the radiation pattern, then how can you change the resultant radiation pattern from a bunch of these antennas if you can't move any of their individual radiation patterns? And the answer, of course, is with positive and negative constructive interference. So we can make the wave add up in areas where we would like it to be, and we can make it cancel out in areas where we don't want it. So the trick is figuring out exactly how to do that. But first, let's try to understand on a more intuitive level. So this animation is showing as we steer a beam all the way across our antenna. However, notice that we don't have just a single beam coming off the front. We have these little side lobes off of the side. And those will always be there, so especially in a real array. This is one of my favorite animations. So what I want you to do is look at the bottom where the waves are coming out, starting from the left, and watch as each of those colors sort of like it's peeling off from the antenna. So as the leftmost antenna begins to radiate, the next one, once the wave sort of catches up to the one next to it, then it starts. And you sort of follow this time-delayed pattern all the way down the row of antennas. And by changing that timing, you can change where this thing is steering. Another good way we can look at it is you can do this in mechanical waves too. So this is 2 drops of water that are falling in phase. So this is sort of simulating 2 antennas that are being excited in the same phase. And if you look right down the middle there where that green arrow was, that's our main beam. And you can see where there's nulls off to the side where we have deconstructive interference. And we also have 2 side lobes in this case on either side of it. In a real phased array, you almost always have more than 2 antennas. And there's a lot of ways you can cancel out side lobes and lots of other effects that you have. So now if we want to steer the beam around, we can make these droplets go out of phase with one another. And now if you watch that constructive interference in the front there, you can see it physically moving left and right as you change the timing of those 2 drops. So that's sort of the basic idea of what's going on an intuitive level. If you take this to the extreme, just for fun, I want to show you guys what you can do with this if you have effectively infinite money. So this is the Seabased Xband radar. This is an old oil platform that the US military bought, and they put an enormous phased array on top of it. This phased array has 45,000 transmit-receive modules, which means at least 45,000 antennas. It is both electrically and mechanically steerable, which means you can actually get a wider field of view than you could if it was just electrically steerable. I do not know what the transmit power is. I got a feeling it's classified, but the statistic they like to throw out is that if you put this thing in Virginia, it could track a baseball-sized object over San Francisco. And so they stick this thing in the middle of the Pacific Ocean and basically just watch everything that everyone puts, into air or space. This is Eglin Air Force Base Site C6. This is one of the first really big phased arrays ever built. The military, as you can tell, has been doing this for a really long time, and they're very good at it at this point. This thing has a radiated power of 32 megawatts, which, as far as I know, is the most powerful radar in the world. I don't know if that's absolutely true, but the statistic they give you for this one is that it can detect a basketball-sized object 25,000 miles away from Earth. So to put that in perspective, the space station is about 250 miles away. And this phased array also has its own power plant and its own fire station. And if I ever design something that has to have its own fire station, that's how I'll know I've made it. Okay, last one. This is a Patriot Missile. Patriot is an acronym, and the first two letters, PA, is phased array. Phased array track to intercept of target. And they have a little phased array on the back of their truck there. By the way, notice, this will come in later, how it's designed. The antennas are in a big plane, and all the electronics are right behind that plane. That's a very common technique, and we'll talk more about that in a moment. Okay, so when you're designing a phased array, you basically have two architecture choices. One is passive, and one is active. So a passive phased array, their nomenclature is a little weird. We mean that we have a single frequency source that we're splitting out to all of our antennas, and each antenna has to have its own phase control, otherwise it's not a phased array. If you really want to save money, you can group your antennas together and have, say, a block of 4 antennas all have a single phase control, but you get worse resolution. The other option is to use an active phased array. An active phased array moves all of the RF electronics. Each antenna gets its own set of electronics, so each antenna can control its phase and amplitude and frequency. And the reason this is nice is because, especially for radar applications, if you want to scan multiple parts of the sky at the same time in multiple frequencies, so you get different resolutions, you can do that. So I think the majority of modern military radars use an active phased array. However, like I said, those are expensive. So we're going to focus on how to build a passive phased array. So again, passive phased array, look at the red box. That's our frequency source, and then we have some network to split that all out, and then each antenna has its own phase shifter, and then we've got all the antennas. Active one, instead of muxing out all of our RF signals, we're muxing out our control signals, and then we replicate all the RF electronics on every port. So if you want to do both transmit and receive on your phased array, you need a way to switch in between your antennas to do that. The two most common ways of doing that are with a circulator or a switch. So a circulator is this really freaky thing it's passive, and using ferrite and magnets, it has this interesting feature where you can input RF into port 1, and it will come out of port 2, and none of it will come out of port 3. And if you put anything in port 2, it will come out of port 3, and none will come out of port 1. And if you put anything in port 3, it'll all come out of port 1, and none come out of port 2. And the isolation between those ports can actually be quite high. So a lot of times you'll see this on your transmit, receive, and antenna circuits. You can also just use an RF switch. Of course, it has to be an RF switch. You can't just put in a relay or a regular transistor because it's not going to work. Okay. So how do we know how to line up all of these phases exactly right so that we can steer the beam in the direction that we want to go? We're going to invoke this thing called the principle of reciprocity, which is, in electromagnetics, it means a lot of things. For this talk, what we mean is the antenna is equally good at transmitting as it is receiving. And it also means that all of the math we're about to go through, which is not very intense, don't worry, will work the same for transmit as it does for receive. So we're going to start by thinking about the receive case, and then we're going to flip it around and show how it works for the transmit case. So up in a corner here, we have our plane wave incoming, and in this case, we're looking at 3-element array. the elements are all equally spaced apart, and we're assuming isotropic antennas, which means they transmit and receive equally in all directions. So our wave propagates in, it hits our first antenna, continues propagating, hits our second antenna, continues propagating, hits our third antenna. All right, so let's rewind at the beginning. The wave hits our first antenna, and it hits it at some angle that we're going to call theta. So if we want to figure out how far the distance is from that wavefront to the next antenna, it's just d sine theta. D, the distance between those two antennas, because and theta is that angle of attack, if you will, and it's just because there's no triangle right here. All right, so now if we want to figure out the time delay it's going to take for the wave to get to the second antenna from the first, we'll call that tau. That's just distance over speed. The distance we just calculated, the speed is the speed of light. So when the wave hits the first antenna, there's some delay tau, and then it hits the second antenna, and then there's some delay tau again, and it hits the third antenna, and so on for however many antennas you have. So that means if we call our wave S of t, then we can write that as a delay at each of these other antennas. And that means our receiving array is literally just receiving the sum of what it's getting at all these antennas. So that's S of t plus S of t delayed plus S of t delayed by twice that much. Now, for the transmit case, what we want to do is decide what theta we would like to steer the beam in a particular direction. And so in this case, y of t is our sort of goal that we're trying to generate, and S of t is this wave we're transmitting out of each of these ports. So we're going to skip some of the simplification and go straight to the formula, which is this. So there's sort of two steps to this. If I say I have some linear array and I would like to steer at some angle, let's say 25 degrees, then, and I want to know what phase shift do I need to send out of, let's say, antenna 10. And you say, okay, so 360 degrees times d, how far apart are all of your antennas? They're 3 centimeters, okay. What angle do you want to steer out again? 25 degrees, all right. And then what's the frequency that you're transmitting? That's lambda, the wavelength. So you take that number, and then you multiply it by the number antenna that I'm interested in, so in this case 10, antenna number 10 minus 1. And that number is probably going to be much bigger than 360 degrees, but a phase shift between 0 and 360 degrees is the same thing. So we just take that number, mod 360, and we get a result between 0 and 360 degrees. So what this means is that for whatever angle I want to steer out, you can easily calculate what phase I should shift in to each of these antennas to get that result. The caveat, of course, is that we are looking at an example here of a linear array of isotropic elements, which is probably not what you will build, because no one can build an isotropic radiator, and there's other design reasons why you might not want to do that. So when you design one, you should use Array Tool, which is this thing written in Python that's great. It will calculate the angles that you need, and it will even show you visualizations of the resulting radiation pattern, which is really nice because normally tools that do this are super expensive. If you have a copy of MATLAB, specifically the MATLAB Phased Array Toolbox, that will also do this. So maybe if your school or work has a copy, you can borrow it. So to actually build one, these are the parts that we need. We need some antennas, we need a VCO, voltage-controlled oscillator, or some sort of synthesizer to generate what we're going to transmit. We need some splitters, we need some amplifiers, and then we need some way to control phase. I'm going to call out a bunch of parts on here if you want to build along. At the end of this talk, I'll have a link to the slides if you want to download them now and check it out. But these are all going to be mini circuits parts. If you've never done a lot of RF stuff, Mini Circuits is a company that makes a lot of RF parts that you can't get on like Mini Circuits, Mauser or DigiKey. And the ones I'm calling out specifically are screw-together parts. So they are between $50 to $150 each, which can add up. But they're almost impossible to screw up because literally you just attach them together. You don't need to do any RF routing or anything like that. And you can build a 4-port array for under $1,000. And of course, if you decide to do this with chips instead of with screw-together parts, you can make it way cheaper. You can also have a much larger degree of freedom for whatever you're trying to design. If you do that, of course, you need to make sure you're following RF routing procedures. Your stack-up matters, your material matters, your trace width matters, all that stuff. That is out of the scope of this talk. But I think 2 years ago at this conference, Michael Ossman gave a talk on how to do basic RF stuff, so you should watch that. And that'll explain probably most of what you need to get this to work. So antennas, the two most common antennas that people use for this kind of stuff are patch antennas and Vivaldi antennas. That's just because they're directional. So again, if you remember that back to that picture of the Patriot Missile or the launcher for it, the electronics are all behind all the antennas, and if you have a directional antenna, that means you're not wasting any of your energy radiating back into your electronics, which is probably not going to be great for them anyway. And Vivaldi antennas are nice because they have an extremely wide bandwidth. So if you want to do a lot of frequency work, then they work well for that. Both of these designs are also pretty easy to find designs of online already. So especially if you're using like an amateur radio frequency or an unlicensed frequency, you can probably find an antenna someone has designed that will work. And because the feature size isn't super small, it's pretty easy to etch it yourself if you wanted to, and it's going to work decently. VCO, voltage-controlled oscillator, this is the thing that's generating the frequency we're going to transmit. You need to think about the output power of this thing and the frequency range. The frequency range is obvious enough, depending on whatever you want to do. The output power, it's best to work from what you want to radiate and then work backwards. Because the problem is, if you buy one of these things and don't think about exactly the power levels at different stages, you're splitting this thing however many times you need to get the number of antennas you want to build. It's easy to end up accidentally blowing up a part because you put too much power into something. So keep that in mind. Splitters, this is a common screw-together splitter. All these things are just passive. So there's a lot of passive components you can use that will do this. If you want to save money and play around with some microwave design stuff, you can implement what's called a Wilkinson power divider. And because it's completely passive, you can literally design this thing just with traces that are exactly the right dimensions and a couple resistors. And you can take one signal in and split it into however many copies you want. And it's free except for resistors, and assuming you get it right on the first try. Amplifiers, obviously there's a lot of stuff you need to take into account depending on what you want to do. If you're trying to send information, you want to make sure it's not going to be too distorted by the time it gets to your antennas. You also want to make sure that you have enough bandwidth, that if your gain is super high, you can have stability problems. This amplifier that I've listed here, for many circuits, for hobby purposes, can be used as both an LNA and a PA. If you string together this whole mini circuits thing that I've been showing parts for, you'll end up with an array that transmits at 2.4 gigahertz and outputs, I think, like 20 dBm or something. So it's not super high power, and for just playing around, it's fine. Okay, and lastly, and most importantly, we need to shift the phase somehow. So you can buy a part called a phase shifter, which will do exactly that. The bad news is that phase shifters, up until recently, have been used mostly for military or aerospace applications, so they're kind of expensive. And by kind of expensive, I mean a single chip could cost between $20 and $50. So it's not like, eye-watering, but it's bad. So instead, you can use a part called an IQ modulator, and those are really cheap. You can get those for like $5. And I couldn't find, Minicircuits doesn't make a part for that. However, you can buy this dev board from NXP that is SMA on both sides, and I think it's like $100 or something. IQ modulator, again, we don't have a lot of time to go in depth on this, but it's two signals you can use. It's used a lot, especially in baseband RF stuff. This video will explain all. This is by W2AEW, who has an insane collection of videos on YouTube that are all extremely high quality. He does a great job explaining exactly what an IQ modulator is and demonstrating it and showing you how to use one. But the point is, you can use this to put any modulation on the wave you send through it. That means you can put any phase shift you want into your wave. So when you're actually designing one of these, there's a couple things you need to think about. This is probably less relevant if you're doing this as a hobbyist project, but start small. It's unlikely you're going to charge in building a 1,000-element array. But build one port first. Make sure that you can move phase around and that the power output is what you expect. And because the way these things are designed, it's inherently modular. So you build one port that works, great. Now you just make however many copies you want and hook them all together. Feedback and coupling is a huge deal because you've got a whole bunch of RF electronics and a whole bunch of antennas that are all really close together, which means the antennas are going to couple into each other, and if you don't watch it, the output of one of your ports can couple into the input of another, and you get positive feedback, and stuff will blow up. You should watch out for backplane radiation from your antennas. Even if you're using a directional antenna, you may think, oh, my patch antenna, it only transmits in this direction. It's fine. But actually, there is a small amount of backplane radiation on the other side of the antenna. And if your electronics are right up against your antenna, then you can easily radiate into them and, worst case, blow them up. Best case, swamp your receiver. The best way to deal with that is shielding. Power and thermals sort of go hand in hand. Depends on what you're trying to build and how big it is. If it's small, it's probably not going to be a huge deal, but your amplifiers are going to get hot probably either way. And because you're going to have a lot of electronics jammed together, then you need to make sure you think about, during the design process, how you're going to get heat out of there and make sure that you're not going to be trying to pull huge amounts of current across your PCB. Isolation, this is different from feedback and coupling because in this case, we're talking about if you're building a radar, for example, it's very easy if you have a sensitive receiver to break it if your transmit path couples into your receive path. And again, best case scenario, you can't detect anything because the echoes you're trying to listen to are getting blasted by your transmitter. There's a lot of ways to deal with this. The most obvious way is by making sure that neither one is on when the other is on. Linearity is a big deal in your phase shifters. Of course, nothing works the same over all amplitudes and frequencies, and that includes phase shifters. So when you're trying to shift phase and you're sweeping your frequency around, you will find that your phase isn't shifting in exactly the same amount as it was at a different frequency. So a lot of times people deal with that with like calibration tables, and they'll calibrate out what that change is and then compensate for it. Same thing with amplitude. And then an extremely practical thing, SMA versus RP SMA. All of the parts I've called out so far for mini circuits are all SMA parts. And if you decide to use antennas from like Wi-Fi, for example, those will all be RP SMA. And it's really dumb that somebody decided to do this. But they have opposite polarity on the inside. That's what RP stands for, reverse polarity. And they'll screw together perfectly, and it will seem like nothing is wrong, but everything is wrong. And so you need to buy adapters for it, and there's 2 different adapters. There's one that goes male to male and one that goes female to female. And it's good to just buy a bunch of them because they're cheap. And at some point, when it's 3 a.m. and you screw in an antenna and it's not working, you will realize that you need one of these. One last thing to think about that's slightly more advanced is this thing called grading lobes. So once you try to steer your beam all the way to the edge of the maximum angle that it can steer to, then it can wrap around on the other side and you can end up with a beam where you don't want one. And the way to fix this is by antenna element spacing. So you need to make sure your elements are as close together as you can get them. It depends on the wavelength, but if they're spread really far apart and you start to see lobes appear where you don't expect them, that might be what's happening. These are, believe it or not, the only 2 like decent links I could find online for building a phased array. There's not a lot of people, I guess, who have tried to do this yet. The first one is a project that's sort of like a phased array. They're working on a receive version with a whole bunch of RTL SDRs stuck together. And the second one is Greg Shervatt's project for doing synthetic aperture radar in his garage. And in general, Greg Shervatt's stuff is really useful. He also did the MIT coffee can radar, if any of you guys are familiar with that. Another option you have if you don't want to use mini circuits is this company called X Microwave, which is super cool. Normally, it would be impossible to breadboard any RF parts because of lots of reasons. So they figured out a way to sort of make it work, and they don't make individual components. They make these boards that have all the correct RF routing done on them, and all you got to do is basically screw them into this giant ground plane, and they have all these little connectors that make sure there's very little loss as you go from board to board. So they make a lot of blocks with parts that Mini Circuits makes, but also parts that other people make. So maybe you find a component from like Analog Devices or something that you like, but you don't want to work on the RF layout for it, or you want to test it out or whatever, then there's a good chance that these guys make it, and you can buy a couple of them and stick them together. The pricing on this isn't insane either. I think it's roughly on par with Mini Circuits, at least for most of their stuff. Here's the sort of quick screw together one that I was just talking about with Mini Circuits. Here's our VCO. Here's splitters. So I only had 1 to 2 splitters, so I had to use 3 of them to get 4 ports. Then we've got IQ modulators, and the reason these all look different is because they're different dev boards that I happen to have laying around. These are amplifiers, just a PA from Mini Circuits, and then antennas. Now, if you build this for real, you shouldn't build it so that it looks like this. This is laid out flat so that you can see it more easily. And you probably don't want to use dipole antennas, depending on what you want to do, but this is just sort of to show roughly how it goes together. And it's really not that many parts. So the good news is this should very soon be getting all much cheaper and easier because 5G includes a ton of phased array stuff. So in theory, in like whenever 5G gets fully rolled out, which who knows when that is, cell phone towers will all have phased arrays in them. And that means there's already a lot of companies that are working on silicon that do that. And so you can buy now chips that are designed for 5G phased arrays. The bad news is they're still a little expensive. We're talking single quantity, like $200 to $300 a chip. However, they're still in really low quantity. No one is building thousands of 5G cell towers yet. So I expect in the next, hopefully 3 to 5 years that this stuff will come down in price a lot. And a lot of these chips actually have a lot of stuff built into them. It's really cool. So all you have to do is literally connect the antennas to them. Most of them will do 4 ports at once from a single QFN part, so not even that crazy of a package. They have phase shifters already in them. They have amplifiers already in them. And of course, they're designed for data, so everything is supposed to be really linear and isolated inside of there, especially given the data rates they're talking about they're trying to achieve with 5G stuff. Other things you can do, you can build your own synthetic aperture radar, that's SAR. So that's an image that Greg Shavat took in his garage of a little model, like F-14 or something. And the basic idea of synthetic aperture radar is that normally radar you are transmitting out and then listening to echoes, but if you can physically move your radar as you're taking images, you can get another dimension out of it. And so they used to do this by putting a radar in an airplane and flying it over, or you can mechanically scan it, or you can use the phased array because now you can shift your beam around without moving anything. You can also do communication stuff with it, which is what 5G is trying to do, spatial multiplexing, super high gain, high directivity stuff to serve individual clients. There's a lot of really interesting stuff that you can do. So the good news at the end of this is that there is one chip that I have identified that is not supposed to be used for 5G. It's not supposed to be used for this at all. But if you abuse it in exactly the right way, I think it could be a really powerful phased array on a chip. So some phased array chips actually will put the antennas on the package. So you can buy one chip that has everything inside of it, including the antennas, and all you have to do is solder it on a board and send it the right data for what you want to transmit out and receive out, and it will do the rest for you. So the one that I found is actually quite cheap in single quantity. Like I said, it was not designed for this at all. It was designed for communication over short distances. And it's a 60 gigahertz, which is very high frequency and would be effectively impossible to prototype at home unless you were willing to spend at least several $1,000s on stuff on eBay to do testing for that. SMA doesn't work at 60 gigahertz. Even the connectors you need are crazy expensive. So it's still early stage. Been talking to them a little bit, looking at some data sheets and trying to make sure that it's actually possible to abuse this in the way that I want to. But if you are interested in taking a look at that, then I could use some help with some FPGA stuff. Could really use some help with integrating it into GNU Radio. And the dream would be to have a little USB stick that's got this chip and a cheap FPGA on it that you can drag a block into GNU Radio and then have your own little phased array that fits in your pocket, which would be super cool. And of course, there's not much that I can offer you in return except for potentially the promise of dozens of people being very excited about it. I actually think a lot more than dozens of people would like it. And I would also think be a good way to get more people who don't know how scary RF can be is. I don't know if scary is the right word, but intimidating. If you get them early, then they may not realize that they're going to spend the rest of their career staring at test equipment trying to figure out why nothing works. Anyway, so if you want to get the part numbers for this stuff and check out those links, then this link is live now. And if you're interested in maybe building this thing, then you can email me there and let me know. But yeah, thank you.